Welcome back to the video lectures of mechanical vibration. In the last video lectures we have seen the damping vibrations, that means free damped vibrations. What are the different damping bodies we do have, right? And after that we have derived that equation of motion to describe to characterize the damping system. In this case, after we have seen that depends on the damping ratio, that's going to be epsilon is equal to C by Cc. From this equation, this is going to be the damping coefficient and this is going to be the critical damping coefficient. This damping coefficient at one point it will convert into the critical damping coefficient, that's already we have derived. So when this value is going to be changes epsilon. If the epsilon value is going to be greater than 1, we can say that system is going to be over damping system. When epsilon is going to be less than that is equal to 1, then we can say that is going to be critical damping. When epsilon less than 1, we can say that's going to be the under damping system. On this basis, and today's topic is the critically damped system. Just before we have discussed the critically damped system is epsilon is equal to 1. So as we know that radical values of that one, lambda and the roots of the radical values, that's going to be that epsilon equal to 1, the radical values are going to be equal. C by 2m whole square is equal to k by m. So then after the simplification, C by 2m is equal to square root of k by m is equal to omega, and this is going to be the natural frequency of that system. So then in this case also we are going to be finding what is the displacement and what is the velocity, so that we are going to be calculating the A1 and A2 values. As we know that the displacement equation for the damped vibrations is going to be x is equal to A1 e to the power of lambda 1 t plus A2 e to the power of lambda 2 t. So in this case we are going to be finding the lambda 2 and we have to define the A1 and A2. So then in this case the roots lambda 1 and lambda 2 are going to be equal to each other. Then how these two are going to be equal to each other? Then we know that the lambda 1 is equal to, what's the formula would you have? Minus epsilon plus square root of epsilon square minus 1 omega n t. Right? And then we are substituting the initial conditions to this system to identify the A1 and A2. Then if I am going to substituting the t equal to 0, so then what will happen in this case? So then finally we are getting the value of this going to be lambda 1 is equal to lambda 2 is equal to minus epsilon omega n. Already we know this is going to be the 1 and then this is equal to minus omega n. So once I am going to be substituting in this equation, that means in this equation, then I will get this one. That's going to be x is equal to, this is going to be the displacement of the amplitudes of the critically damped system when it got the external excitation. So that x is equal to a1 e to the power of minus omega nt plus a2 e to the power of omega nt. And if I am going to be deriving with respect to the time again, so that I am going to be getting the velocity component also. So from that one we are going to be identifying the a1 and a2 values. So as for the displacement of the vibrating system, that's we converted into the graphically after the experimentation. So in this case we can see here the x-axis is going to be representing the time period and the y-axis is representing the displacement of the system or amplitudes of the vibration. There we can see here the graph is started to move from the upward directions, then slowly it is going to be decreases. So what it is representing here, when the time is going to be increases from this side, so then what happened at certain point it's going to be reached to the maximum displacement of the system. After that it's going to be energy started to dissipating, right? And it will take some more time to settle to get back to its equilibrium position. So this way we are going to be calculating the critical damping coefficient system, how it is going to be behave. So but when we are going to see over damping system, so then the system is going to be in this direction. So this is the displacement. So then what happened? It's going to be like this. In this way. This is going to be called over damping. So can you see the graph between these two? In the initial stage of this critical damping, it reached to the maximum position. But in this over damping, it reached to the maximum position. Then the energy started to disappear through the damping body. So then this is the difference between these two and representing the characteristics of the over damping as well as the critical damping system.